Our next speaker is Dimitrios Oikonomou, who's a co-founding partner and CTO from Earth Science Analytics. That's our new brothers in arms coming into IMDEX. So we're very excited to have them on board as our one of our latest acquisitions. Dimitrios leads the technology strategy and development of cloud, data lake and AI-driven geoscience solutions. With a PhD in electromagnetics and over 20 years of experience in software engineering, machine learning and subsurface analytics across oil and gas, CCS and renewables, he's authored more than 24 publications. He specialises in scalable cloud platforms and AI for geophysical and wellbore data, bridging domain expertise with digital innovation. So welcome, Dimitrios, to the panel.
So first I want to thank Dave. Dave, I met him right after the acquisition in August, and he told me, okay, really nice to meet you, but you have to come in Vancouver and give a presentation. So that was the first discussion actually we had with Dave. So, and I told him yes. I would. Yeah, I told him it's my pleasure because I enjoy such things. So, as you mentioned before, my PhD is in electromagnetics and linear accelerators, quite different from what I'm doing now. So then I went to defense, and around 2012 I went into the oil and gas industry. So that was a nice beginning for me. Why? Because suddenly I saw things totally different. You know, I'm coming up from engineer and meeting geologists and geophysicists who actually are visionaries, mostly visionaries, because they try to solve the impossible. It was for me very, very fascinating. So, and I have been working on the oil and gas industry, and around 2015, it was when actually in the company I was there, we managed to have the oil and buoy discovery. And right during this process, I had one of my co-founders in Earth Science Analytics asked me and tell me, okay, can we go and try to find the shear velocity of this wellbore, how to find it, how to calculate it, do some modeling. And he drive me to different geophysics methods. And I told him, okay, but I need to find this parameter and this parameter. He told me, go to find the papers. It was impossible. I told him, okay, let's try with machine learning. Let's try to see what's happening. I know the uncertainties you ask me to bring, maybe they are not, they are giving more errors than I would have with the machine learning model. And it took me, I think, more than a month to persuade him that, okay, what I delivered to him is probably better than what he was trying to do himself. But when he did this, then he said, okay, we have to make a company on this. And the journey of this company started, and today we are with IMDEX. And what we are doing in this company, actually we have built this platform, we call it EarthNet. And EarthNet is a cloud-based application, cloud agnostic, so we can deploy it in every cloud provider. Provides no-code ML, so it means the geoscientist is able to do his machine learning and his workflows without needing to know anything about this, but he has full control of what he is doing. He has all the metrics to understand how the models works, and also provides in the companies the assistance that when we have a data scientist who is able to provide the model, he can just push it into the application and deliver it to the crowd, to the people on the floor who are doing the actual jobs. And of course, it is able to work with a large scale of data. In oil and gas, we have seismic data on the range of terabytes. So a seismic volume can be 1.5 terabyte, and if we're using 5 of them to do something, we might have 9, 10 terabytes that we have to process. And it's able to follow what's happening and as I said before, be a good collaboration platform. So people are working on the same projects without the need of duplication to allow keeping data storage and minimum. Cloud is expensive, so you need to be able to do everything cost efficient. So And then I come to this question, because we discussed about questions before. So why digitalization and AI matters? Why it matters when we are doing subsurface characterization? And actually, this is, in this slide, I try to give some my view on this. So when we enter the oil and gas industry, and I believe it is very close to what's happening in the mining industry, is that we have a lot of data. The amount of data we have is enormous. And sometimes this is good, sometimes this is problem. Why? Who wants to go and load everything? Where can I find them? And if I can find them, can I process them? So if I'm on my workstation and I have 32 gigabytes of RAM, how much can I load here? So can I go to the cloud, and then where should I put them? And where the data are? So this actually is the first pillar. So we have a lot of data, and actually it is very seldom that we are able to use all of them. Very seldom. So very few of us is able to find all the data. The second thing is that we have many disciplines. And as a result, what is happening? I am working only with the wellbores, and another is making surfaces, and another is making the model. Each of us is providing something. But now we have to go to multimodal. All have to work together to provide one thing. It's not possible that we have people sitting in their office and doing something and not working with the other who is working on the same subject. We are working with the same ore body. We have to see everything and use all the information in order to collaborate and get the best results. So having fragmented workflows actually don't allow us to get the best out of it. And the result of this, what is the result? That we have either incomplete or biased understanding. So if I have if I'm sitting alone and I'm working with a part of my data in my office, and I have a wrong impression of something, or if I don't know what's happening in the next lab, then I might give some outcomes that are actually biased by me. So therefore, what does it mean that we have suboptimal exploration and suboptimal production strategies? So it is important that when we say that we are making decisions based on data, that we are using all this data. And all this data in a collaborative platform, not fragmented. So, and how we are trying to solve this in Earth Science Analytics. What does this platform is doing? So, as I described before, EarthNet is a large-scale integrated data analytic platform and consists of the following basic tools. So, in the middle is the EarthNet data lake. What is the Earth data lake? EarthNet data lake is actually a database that is pointing to data that exist in different data sources. This can be in Azure. I mean, we have data in Azure blob storages. This can be, I put also names from the oil and gas. Seagull is one company that provides a lot of data in the oil and gas industry. This can be in OSDU, in Google Cloud, in Delphi, where they are. It is not possible that we consider that we transfer everything to the cloud. Some might be in our local storages in our company. But we need to know in one place that all this data, where they are, where they exist. And if we have this certain data lake there in the middle, then we can hang below different applications. And we have built the following 5 ones. It is AI images. You understand what it is doing. It is working with cores, with chips. We have built EarthNet AI wells, which is actually 1D property prediction. So we are working with the wireline logs and try to make predictions and fill in other curves. We have built the AI seismic properties. It is on 3D now calculations. AI seismic interpretation, faults, horizons, automatic interpretation of structural geology, and finally, maybe most important, earthing sites. And what is the earthing site? It's actually the tool where we are making queries on the data we have delivered on the left in order to understand what is happening. I was thinking how I will continue the presentation when I've been working on this last week, and I thought the best is actually to give you some examples. Otherwise, you will lose me very, very fast. So what I did, considering also the title of the session, Optimizing Data for AI, I'm starting with this one. And this one, actually, I took it as something we have, this slide more or less have we built more than 6 years ago. And I like it for two reasons. Because you see it is 1, 2, 3. And if you take one and 2, it's actually 70% of the slide if you go from left to right. And this is actually very important. Why? Because it is monitored that the work we are doing, when we are trying to accomplish a task, 70% actually we lose on trying to collect the data. And only 30% we are doing for the job. And I have seen in reality it's even worse. Trying to find the data today, it is still maybe 80%, even 90%. So where are the data? Then I get them, and then I can do them very fast. What we are trying to do with the data lake is actually that we verify that steps 1 and 2 is happening only once. We don't repeat it. So we do have to import the data from unstructured databases, harmonize them. We do need to QC them. This has to happen. It is the only way. If we want to train machine learning models, we need to be able to have QC data. We need to know that they are all sitting on the same units. It's impossible to just feed them the machine learning models unless we QC what we have. But we need to be sure that this happens once. We don't have the time to redo it again. And we need to be sure that whenever one of our employees in the company is trying to work with an ore body, everything related to this ore body is given to him without him having to go and search for data. And then we finish with number 3, which is actually the AI and ML. So AI and ML is a small, really small part. Why? Because if you have managed to do all this correctly, step 1 and 2, you go to this stuff. Try different models, make use of the results, and ask the important thing, ask for geological QC. So you can never trust a model itself. Metrics are fantastic of the model, but the geologist has to be there and evaluate the results. Because actually it is the vision of the geologist. I mean, when you are doing, I really I am not just a geologist, but I envy them. Because they are visionaries. They have to build models and they have to evaluate them with data. And then, based on this workflow I have shown before, I will discuss about these missed pay analytics problems that we have done for several customers. We have done it for 4 clients so far. So, and what is this missed pay? This missed pay is actually, that is happening a lot in the oil and gas. I believe also because I seen last week from DataRock one LinkedIn post that it was very similar. So try to find opportunities that actually we have done the job, but we have lost them. We have not understand them when actually we did it. So and this is something in oil and gas is happening a lot. Why? Because drilling a well in oil and gas is very cost expensive. I mean, a well is $60 million, maybe $100 million. So now everybody is trying to see, is there something that I passed because I was looking for something different? So these 4 cases is one from, I think the most important is the first one, Why? Because we did it in 2020. It was more than 5,000 well boreholes. And when you think about well boreholes, each of them is around 30,000 indexes. So we are talking about more than 25 million rows there. And trying to work this data set was not straightforward. But what we managed, actually, we managed to deliver for the combined Norway and UK oil and gas directories some results. And how we are doing this mispay analysis? This mispay analysis happens in the following way. We take the wildlife logs, then we try, because mispay actually we need to find what is the porosity, what is the saturation of hydrocarbons, and then based on this to understand where you have pay intervals, and if you are able to find pay intervals that has not been used, try to do some investigation to see, do they make sense or not? So to achieve this, actually, because the wildlife logs that we deliver are not complete, we have holes or even missing, so we need to use the relevant wells in the basins in order to fill in missing logs or even create them if they are missing. And this is actually what has happened in one of these projects, in the one that we did for Ville-des-Aldea. It is 2,200 well bores. And as you can see, I have two graphs here. So the first row shows that all the well for the acoustic velocity, we have around 6,000 kilometers of well bores. Out of them, 4,500 delivered with data. And what we have to do was to fill in the rest of them. But what is important when we are talking about porosity, FIE, and saturation, actually what has been delivered to us was only 1,700 kilometers, where the rest of 4,000 kilometers were missing. So we had to fill in and calculate them. How? Using AI and machine learning. And by doing this fill-in on the last three properties, porosity and saturation, we were able to provide to the clients pay intervals that actually has been overlooked. And what is this pay interval that overlooked? And this is a real example. Here we're talking about Gullfaks well discovery that happened in 1978, so quite old. So Gullfaks is have been producing for more than 35 years. And you can see here the area. This is actually the sands here. These are the sands that they are producing. You can see here the porosity and saturation here, and have been produced for many years. But then it was going to depletion. So when they found out that, okay, we're running out of this, what we're able to do? So we did the calculation. I mean, these are the original logs we have here from the Gullfaks, actually the wildland logs that we have delivered in 1978. And then when you are doing the mispay analysis, actually what we have seen, that we have here, you can see some sands here. And actually we have seen some responses also there and there. So what was this? Actually by that time, if they have done correctly the job, and because when they found this big discovery, they didn't care about the rest. But actually there was something up here. And this was around another 150 million barrels, which actually they have been working, they saw them. When they started at the end, they were able to see and find out that it was there. And started in 2012, so almost 40 years after, pumping out also from there. And this actually extended the life of the field. Another case similar to this is this one, which is even more important. Why? Because we have one. There was this about the building discovery. There is a well, this 351113, and this was a discovery well that actually found some hydrocarbons down here. And you can see when we did the 3D seismic analysis, we can see them also there. So, but this was not economic commercial. They were not able to, with these only hydrocarbons there, to go and build a platform and start depleting. But by that time, they had, if they were able to see, it was possible to see that, okay, here, there are some sands. And these actually are this Draupner formation, which is a bit shallower. And actually there was a leakage, and from there was accumulating there. And this took around 30 years to go and find out, to understand this. So they had already the signs here 30 years before. And they came up and they drilled this one, and they have now the production from there. So mist pay is really important. Why? Because most of the times there is a small team of people that probably they have some understanding of the field, and sometimes that can be also biased, because we are human. If you don't believe on this, you will not explore any further. But maybe you have signals that you have to go and see what's happening. And the signals were there. So I skipped, because here it is actually the work we are doing mostly in the oil and gas. I mean, these were the most successful product we are doing, but I know seismic is not something yet very common in the mining, but this is very important. Why? Having done the job on the well bores here, we're able to use the partial stacks plus the velocity volume that is used in order to produce these partial stacks. So these 4 plus these are the inputs with a labor, the upscaled log, in order to make a machine learning model that is going to predict 3D property volumes. And with this technology, actually, we're able to produce volumes like the ones you see below, velocity volumes, porosity volumes, saturation volumes, and any other property. So we're able to do the mapping between the seismic to the wildlife logs, and then be able to produce any kind of volume. So I will try to be very fast on the next 2 minutes. So a lot of MLOps. MLOps, I'm saying, what is MLOps for us? It is pre-trained models. You know, this is, seismic interpretation is many times quite boring because it's repetitive. Trying to make a horizon in multi-lines and try to build a horizon takes a long time for a geologist. Today, with the models we have, he actually labels in 3-4 lines, and then the machine learning does the job for him. And we are able to have fault planes, horizons, zonations, and geobodies. I will go to this. I will have more than 2 minutes. It's possible to do it, so I will try to be fast. So this is, I think, very something really nice and important. So here we see, I'm trying to show what we are doing in AML. And this is a project we have done and we are doing, and we call it From Core to Seismic. And this actually is a discussion because we have heard before that we have different resolutions. And this is happening always. And this is an example that we have from core, and the cores can be, it is millimeter, I have the resolution I have, sub-millimeter if I want, to the seismic, and the seismic we're talking about a resolution of 10 meters, maybe 50 meters if you want to be accurate. So in this process, actually what we are doing AI to go from rock samples and cores to do calculations on lithology, for example, and then go and map here the lithology we have done from the cores, use the wildlife logs to be able to have lithology based on the wildlife logs, then use them in the seismic, upscale them, of course, and then try to map the seismic data to the property prediction in order to get 3D results. So actually, we take the data from the cores and we take them to the 3D. And this is exactly how we do it on the images. So we have, for example, the original image. We predict something like this. This means that based we do just averaging, and we find out here that this image down here we have 70% descent and then 30% a mudstone, and all the same for limestone and coal and so on. So actually here we go from samples, we go to the wildline resolution. And this wildline resolution we train in order to produce volumes like this. And what do you see here? This is a troll field. The troll field is actually, you can see maybe the flat spot that it is there and there. So here are the sands of the troll field down here. And here are the coal of the troll field, and here, there, and there. And what you see, actually, these black lines are the results from the automatic interpretation of faults. And what you see here is actually the data we get from the wells that have penetrated there. And then you can see the excellent accuracy between our labels, which are the wells, and the results that we provide in the 3D. So I skip 2 more slides. So what we are doing, I mean, in essence, we provide this data lake EarthNet, and then with a target that we provide the geoscientists all the data. So we say all the data at the fingertips of the geoscientists. And this is actually how we built the company. This is something from 2017. That was the vision. But now this is changing. And why it is changing? Because we are going to a next era. And this actually, all the insights at the fingertips of geoscientists. And why this is important? This is something we are working right now, actually trying to use LLM, but grounded LLM. And what is grounded LLM? Iraya is a company that partly owned by Petronas, and they have provided to Petronas LLM, and they are able to make questions or their documents. And then they come with some results. But many people don't believe them. How can I believe? I can spend time, but my first publication in 1992 had mistakes. Because I sent it, and then while working, I said, oh, I have a mistake. It was not possible to have a panorama, so it is still there wrong. But what we can do now, we have provided, EarthNet provides API, so that the LLM is able to make queries on EarthNet and actually validate the results. So when it retrieves something from the documents and say, okay, in this area I have low saturation, you can ask directly EarthNet, what is happening with the saturation there? And you get actual results. You get the data themselves. Not only the data, but also we are going to the links that you can press, the user can press and come to a page like this, where he's going to visualize the actual data. And then he can believe. And then what he has built and the knowledge he is using is knowledge based on data. It's not a text. It's grounded in knowledge. And here I can finish.